All right, ladies, welcome to the podcast on random variables, the first section of chapter 6. Some of this is going to be review. We talked about discrete and continuous random variables at the beginning of the year. A few definitions we're going to start with before we actually get into looking at some discrete variables. A random variable is exactly what it says right here. A variable whose value is the numerical outcome of some kind of random phenomenon. So a chance outcome, tossing a coin, rolling a die, all those things we've been talking about. When we are working with a random variable, we're going to designate it with a capital letter. Normally X and Y are typically used. And a random variable has a sample space, just like we talked about sample space for different chance outcomes, and it's basically the possible values the random variable can take on. And once you find the sample space, you can assign a probability to each outcome and make what's called a probability distribution. And this can be in a table format, or it could be a graph like a histogram. And I'll show you some examples of both of those. So let's actually put this concept of random variables into play. So we're going to start with a simple example, which is one that involves flipping a coin 3 times. So if I flip a coin 3 times, you all know how to make a tree diagram to come up with the sample space for flipping a coin 3 times. And then this would be our sample space. And then in the previous chapter, we would do things like, what's the probability of getting at least 2 heads? And things like that. Well, now we're just going to get a little bit more specific, and we're going to define a random variable, X, as being the number of heads you get when you flip the coin 3 times. And so these are our possible values of the random variable without the 4. Because if we're only flipping 3 times, the maximum number of heads that can come up would be 3. So in 3 flips, I could get no heads. I could get 1, 2, or 3 heads. So if we look at our sample space, obviously this outcome, we get 3 heads. This one we get 2, this one we get 2, this one we get 1, 2, 1, 1, and then 0. So 0, 1, 2, 3 are the possible outcomes for our random variable. And now what we can do is we can assign a probability. So since the probability of getting heads and tails is even, we know that the likelihood of getting 0 heads is going to be 1 out of 8, because there's 8 possible outcomes, and this is the only way to get 0 heads on 3 flips. The probability or likelihood of getting 1 is going to be 1, 2, 3 out of 8. The probability of getting 2 heads will be 1, 2, 3 out of 8. And then to be a valid probability distribution, all the probabilities have to add to 1. So without even looking, we know this would have to be 1/8. And you can write the probabilities as fractions, decimals, makes no difference. But the sum of all the probabilities has to add to 1. So this is what's called a probability distribution of a random variable. So the random variable is basically your outcome of interest. You think about what values that variable can take on, and then you assign probabilities. Okay? These outcomes for this example are discrete outcomes. So if you remember from about the difference between discrete random variables and continuous random variables. So discrete random variable is a collection of isolated points on a number line. So basically something you're counting. And if you recall earlier in the year, I gave you the example of if I go into Kroger and they stop me and they say, will you help us collect some data? They might be interested at the end of my shopping trip, the number of items that I purchased and are in my cart. Well, the number of items is going to be something countable, and it's going to take on basically integers or whole numbers. Whole numbers for number of items at the supermarket. You can't buy 23 and a third items. It's either got to be 23 or 24. A continuous random variable is when the variable can take on any possible value within an interval. And this is normally when you're measuring something. So it could be time spent in the grocery store. Anytime you are measuring a variable and it can take on a value within an interval, then the random variable is continuous. Okay, so those are the just two kind of reminder definitions for those terms. Here's an example of a continuous random variable. It says an engineering stress test. Pressure is applied to a thin 1 foot long bar until the bar snaps. So here's the 1 foot long bar, and they're going to apply pressure, and it can snap anywhere. It can snap here, it can snap there, it can snap right in the middle. So basically, the random variable is where it snaps from the left-hand side. And so for this one right here, it might be at, I don't know, 0.31. Or if it breaks right here, it might be at 0.6. If it breaks right here, it might be at 0.833. So anytime you're measuring something, the variable would be continuous rather than discrete, but it obviously, if you look at what I have right here, we can only measure to a certain degree of precision, but the measurement can take on any value between 0 and 1, so it's continuous. Okay? All right, let's go back to discrete random variables because that's going to be more of the focus in this section. A probability distribution gives the possible values of the outcome and then assigns a probability or a relative frequency. Remember, that's just a percent. And it can put it in a table or in a graph format, in a histogram. And we did the table before with the coin flipping. And I have an example coming up where it would display the probability distribution in a histogram format. So we'll get to that in a second. Let's look at a second example of a discrete random variable. So suppose that each of 4 customers purchasing a hot tub at a store can choose either between an electric model or a gas model. And the customers make their choices independently of one another. So that means what one customer decides is not going to impact or affect what the next customer decides. And that 40% of the customers tend to buy electric and 60% tend to buy gas. So if we look at 4 customers in a row, one possible outcome would be EGGE. So the first person buys electric, the next 2 buy gas, and then the 4th one buys electric. Okay? Since they're making their choices independently by the multiplication rule, to find the probability of this outcome, we can multiply the probabilities and multiply 0.4 times 0.6 times 0.6 times 0.4. Whatever that ends up equaling. I am not 100% sure what that value would be. But if you plug it into your calculator, you're going to get 0.0576. So there's about 5 to 6% chance that if we look at 4 customers in a row that they would purchase that combination. Well, if we look at a different outcome, EGEG, electric gas, if I go to find that probability, it's really the same thing using the commutative property. Both of these are 0.4 squared and 0.6 squared. So this outcome is going to equal 0.0576 as well. Another possible outcome would be GGGE. Well, to find that probability, we would do 0.6 times 0.6 times 0.6, or 0.6 cubed, times 0.4. So this is just your basic straight up probability from the previous chapter, and this would equal 0.0864. So this part is nothing new. It's straight up probability. But what we're going to do in this scenario is we're going to define X, our random variable, to be the number of electric hot tubs that are purchased by the next 4 customers. So what I've done on the next slide is I've created a tree diagram so that we can make it visual. Okay, so here's where we are right now. We have the probability for 0 and 4. What they did is they ordered all the outcomes of one electric purchase together, and these probabilities are all going to be 0.4 for the one electric customer and then 0.6 cubed. And so that's, if you add up 0.0864 and multiply it by 4, you're going to end up getting 0.3456 for one customer purchasing an electric model. And then if you do the same thing for 2 and 3, so here, let's just do 3 real quick. All of these outcomes have 3 electric purchases, so that would be 0.4 cubed times 0.6 for the single gas purchase, and that probability is 0.0384, and then if you multiply that by 4, you end up with 0.1536, and then by default, to get the probability for 2, you could just add the probabilities in the table and subtract from 1 and get the 0.3456. So this is our probability distribution for X. So now if we want to find the likelihood or the probability of 2 or more customers purchasing an electric model, we could just sum up these 3 probabilities and it would be 0.5248. When you're interpreting probabilities in a probability distribution, you have to remember that this probability is based on what would happen in the long run. So in the long run, if we repeatedly looked at 4 customers in a row, 15% of the time, exactly 3 customers would purchase electric spas. All right, so moving on, a few principles of or properties of a discrete probability distribution. Each individual probability has to be between 0 and 1, and that should be pretty intuitive or common sense. And then I've already illustrated this in the examples we've done. The sum of all the probabilities in the probability distribution has to equal 1. If it doesn't, it's not a valid probability distribution. So let's finish with just a few more examples. So for this one, a consumer organization evaluates automobiles and the number of major defects on each car. So X is the number of major defects on a car, a randomly selected car of a certain type. A large number of automobiles were evaluated, and the probability distribution is consistent with the observations. So here's our probability distribution. Boy, I hope I don't buy a car and it has 10 major defects, but the likelihood of that's pretty small. So the first question, is it a valid probability distribution? Well, if it's valid, each individual probability has to be between 0 and 1, and the sum of all the probabilities has to equal 1. So if you hit pause and you take a few minutes and if you added up all these probabilities, if they equal 1, it's a valid probability distribution. And according to my records, it does not equal 1. So it is not a valid probability distribution. You'd have to add 11 plus or 11 or more to kind of complete the probability distribution so that it totals up to 1. We can, however, use this probability histogram. So instead of making a table, you could graph. So here are the discrete number of defects, and then on the y-axis is the probability or the relative frequency. So you've got defects on the x-axis. And so if I want to know the number of major defects between 2 and 5, inclusive, so that means including 2 and 5, we would just add 0.209, 0.223, 0.178, and 0.114. Okay, and that would be the probability of the number of major defects being between 2 and 5 inclusive, whatever that ends up being. Here. One last concept, to find the mean or the center of a discrete random variable. Okay. The notation we're going to use is mu sub x. So you're familiar with mu for mean, and then the sub x just means the mean of the random variable. And it's basically where the probability distribution would be centered. And what it is it's a weighted average. And then you have to remember it's the long run average. It's what the average would be in the long run. Another notation we sometimes use is E sub x, and that's called the expected value. So the expected value and the mean of the random variable are the same thing. And what you're going to do is you're going to use this formula because it's a weighted average. You're going to take each outcome of the random variable, multiply it by its probability, and then sum them all up. And the formula looks more complicated than it actually is. So let me just show you an example. And this is on your formula sheet. So there's no need to memorize this. Okay? So let me show you an example with actual numbers. So if I had a probability distribution as follows, that talks where the random variable represents the number of children in people's families. So some families have no children, maybe just a married couple, and I went up all the way to 6. To be a valid probability distribution, all these probabilities would need to sum to 1. So this is 12, 32, 42, 72, it works. They do all sum to 1. So if I want to find the expected value or the mean of the number of children in the family, here's what I would do. I would take the value of the random variable and multiply it by its probability. Take the next value of the random variable and multiply it by its probability. Take the next one, 2 times 0.28. The next one, 3 times 0.2. The next one, 4 times 0.1, 5 times 0.01, and 6 times 0.01. So I'm taking each value of the random variable and multiplying it by its probability, and I am summing or adding them all up. And if you do that, you end up getting 1.77. So the expected value or the mean of the random variable is 1.77. So we would interpret this as if we looked at many families over and over and over again, we would, on average, each family would have 1.77 children. Now, it's a discrete random variable, but the average can be a decimal. Okay, so if we go back up, I think it's important for you to add here that this can be a decimal. The random variable itself is discrete, and obviously no one can have 1.77 children in their family, but it is a long run average. So that's why the decimal is okay. All right, one last final example. An experiment consisting of a random automobile licensed in a particular state. They define the random variable X as being the number of headlights that need to be adjusted. So everybody's car has 2 headlights on the front of your car, and they looked at the number of headlights that needed to be adjusted. So if the car's perfect, it doesn't need to have any adjusted. Or maybe it has one that needs to be adjusted, or both headlights need to be adjusted. Here is the probability distribution in table format. It's valid because the sum of all the probabilities, 0.5 plus 0.3 plus 0.2 equals 1. So yes, it's valid. And now I want you to find the mean number of headlights that need to be adjusted. So to do that, you just do 0 times 0.5, 1 times 0.3, and 2 times 0.2. So you're taking each value of the random variable, multiplying by its probability, and summing them all up, and that equals 0.07. So the average number of headlights in the long run that need to be adjusted is 0.7. Okay, so last slide, promise. So if the mean is 0.7, if we actually did a sample of 100 cars and found that 46 needed no headlights adjusted, 33 needed 1 headlight adjusted, and 21 of the cars, so we could change those to decimals, 0.46, 0.33, and 0.21, since it's 21 out of 100 cars, what would the sample average be? So if you multiply these, you end up getting 0 times 0.46, 1 times 0.33, and 2 times 0.21. We end up getting 0.75. So how come we didn't get 0.7? You have to remember that this is based on what would happen in the long run. And there's going to be variability from sample to sample. So, as the sample size increases, the closer it will approach or get to the mean. Okay? So the key is that this is a long run average. Okay? We will pick up on the rest of this section and finish up with a standard deviation of the random variable when I see you in class next. Thanks for tuning in, ladies.